So I'm going to talk about the coherent imaging, unification of microscopy, diffraction, and computation. So I'm going to hopefully convince you that actually it's a very powerful method that is really the combined microscopy, diffraction, and computation. So yesterday I already talked about this light microscope. This really play a very important role for the modern science and technology. So this is a piece of cork hand-drilled by Robert Hooke using this microscope in 1670. You can see this actually, everybody, most of you probably like wine. That piece of cork has a lot of compartment. So this is actually a plant cell. Now he found this actually in compartment. He called this cell. Now the idea of microscope actually was first suggested by Kepler, the famous astronomer. In 1611, Kepler suggested that a compound light microscope could be constructed based on the three-lens conformation. Okay, and 50 years later, Hooke built. He is not the first one built, but he built a microscope that studied biological samples and all kind of different insect, different kind of samples. If you have a chance to go to a Huntington Library and the gardens, I strongly encourage you to go there. And then the basic why microscope works, and this is the so-called Abi Theory. It was 1876. Now the Fourier transform was discovered in around 1750 by Joseph Fourier. So this is almost 100 years later, right? And it turns out this is just the Fourier transform. You put an object here at a focal point, it's just a Fourier transform. They can maintain both the magnitude and the phase information. And then far away, basically Fourier transform, inverse Fourier transform, get an image. So Abi actually in this is Abi's grave. This carved on his grave. I hope some of you eventually on your grave can have something carved there. So set your bar high. Okay, I know some of the students. Hopefully, on your grave you can have something engraved. So this is d equals to lambda divided by 2n sin alpha. So lambda is a wavelength. D is the resolution. The resolution of the lens determined by lambda divided by 2, n and the index refraction of the lens. Okay, and the sin alpha is the angle. This angle. The angle extended by the half angle extended by the lens. Yes? Is
that not the refractive index of the medium directly before the lens?
This refractive index, the media's, yes, media, yeah, right, yes, media, yes. This is actually media. This is why for some nowadays, for biological imaging lenses, you have to use oil. So oil to increase n. You're right, yes. Is it correct? Any question, please ask, okay? So over the last more than 300 years, this actually Abi, that's no resolution image, and recently super resolution. Super resolution just like, to me, is just a localization technique, basically, right? And so that's a microscopy. So kind of, okay, I give you some overview because I want to hopefully convince you the combination microscopy, diffraction. So diffraction, we can trace back to the X-rays. The discovery X-rays in 1895 by Röntgen. So Röntgen was a professor in University of Würzburg in Germany. He was very, German. That's how they're very rigorous, right? So he's working on some using electron beam bombard some target, some metal target. Okay, he has nothing to do with X-rays, nothing to do with these X-rays. Okay, so every day he shut down the machine and left. Okay, continuously. But one day he made a mistake. He forgot to switch off the machine. That's the machine. And then second morning he went in. He found the film in the drawer. The drawer actually, the film actually kept it in an envelope, the thick envelope. He found that all the film exposed. He found that it never happened before. Only one thing, the machine was on, the film is exposed. So he said, very interesting. He didn't see anything come from the machine. So he repeated, turned the machine on, film leave there, and actually the film exposed. After a while, film exposed. So this is why he asked his wife and put hands between the machine and the film. So this is the wife of the hand. For the first time, actually, humankind see the bones of live people. The dead people's bone means so you can alive people. And also, there's a wedding ring here. I mean, all this is because X-ray is absorption coefficient, right? The bone has a high absorption coefficient than softer tissue, and then metal, actually gold has a very high absorption coefficient. This is actually one of the most famous images ever taken in the history of science. One of them, I think it is still, I mean, Röntgen got first Nobel Prize in physics. So that's the discovery X-ray. So why is it called X-ray? Because there's no X-ray. Usually X means available, unavailable. That's the math we use, always X-ray. X, right? So this is what the X-ray, there's no what it's invisible, X-ray invisible. And you just see, you can get exposed, but nothing else. And then the physicists were very intrigued. It's very interesting. So this was discovered 1895. And a few weeks later, people in New York already applied for patent because they realized this will be great for the medical physics. We see live people the bone. I mean, it's amazing that just a few weeks, two weeks later, right? And then the physicists try to understand what is X-rays. And then the famous physicist Max van Looy, and he was a professor. He asked it to a student and one associate. He proposed this experiment. He did it. He just want to find out what is it. He envisioned that could be wave. So wave, then crystal. It's an atom has a periodic arrangement, right? So in principle, if you put a crystal there, you could get something. So this is the first X-ray diffraction pattern, or first any diffraction pattern. It's from a copper sulfate. And you can see it's very kind of a bad quality diffraction pattern, but the first, from the original science, always the first one always kind of look bad, but there's some sign here. You can see actually different angle. You can see this discrete peaks. So you can see from physics point of view, from mathematical point of view, very simple. If we transform a periodic function, the periodic function, right? So this is actually a periodic function. And the experiment was done in 1912. So it's found X-ray actually wave, because otherwise you cannot just have this diffraction. So X-ray is a wave. And Van Looy got it, 1914. And then, okay, that's good. X-ray is a wave. Then what is this used for? What we can learn from the pattern? So this is actually done by Bragg, William Bragg and Lawrence Bragg, father and the son. The son at that time did experiment at the age of 23. So basically, if the X-ray wave, we come in, you have periodic structure here. So you get scattering, right? And then if this path should be, if this path is equals the path between this ray and this ray is BCD, that distance. If this distance is proportional to integer number of lambda, the wavelength, and then you have a constructed interference. Actually, he proposes Black's law. The resolution lambda divided 2 sin theta. It's amazing. This equation is the same as the grave of Abi. The difference n is index of refraction of air. That's one and one. Right? This is, science is amazing. That's actually the same. And from this equation, actually, just is interpret the X-ray diffraction patterns, and they determine the solidity atomic structure. The first one, table salt. Everybody use it. It's in the textbook. It's in all the high school textbook, and also diamond. The atomic solidity, atomic structures. And they got a Nobel Prize 2 years later, and William Lawrence Bragg. He was age of 25, still the youngest ever to get a Nobel Prize in physics, in science. Okay, so that's kind of the diffraction. And so let's try to understand why this related to my talk. Now let's look at X-ray diffraction by crystals. I mentioned Van Looy, Bragg, William Bragg, Lawrence Bragg, right? If a periodic, one-dimensional periodic structures, it's one unit cell. Unit cell size A. If you take a Fourier transform, okay, this is a Fourier transform, you get magnitude, you get the peaks. Right? Because this is a method very known. If a comb function, take a Fourier transform, it's a comb function. So this is 1 over A. This is called real space, reciprocal space, or called Fourier space. But also, you will find this enhanced by n, and the number of how many unit cells. This is why even at that time, they can measure the intensity from crystals because the interference. Because they have many identical copies of interference, the constructed interference. Right? So if any questions you can ask, okay, I just want to, now there's another very important theory called the Shannon Sample theory. And some of you probably know. Shannon is actually considered father and the founder of the information and digital era. Everybody is digital. Everybody is Shannon Sample theorem. So what is Shannon Sample theorem? So let's say, okay, he was engineered at Bell Lab. Okay, Bell Lab is really, years ago, it's really the best place for physical science. I think LMB, the Laboratory Molecular Biology in Cambridge, that's in biological science. They got so many Nobel Prizes. And Bell Lab, he was at Bell Lab. He was thinking 1940s. He was thinking how to send a signal from one place to another. Digital signal. At that time, all signal sent analog signals. But he wants how to send digital signal from one place to another place. Okay, and let's say signal cannot be infinite long. So let's say this is time t. Okay, this is a. If you take a Fourier transform and get it, you can either send this signal this way. Now, he actually mathematically showed, that's in his paper, actually, very famous, very well cited. I mean, this is really so important. Okay, this Shannon is so important. His theory is, and if A, he just usually send these points from New York to Los Angeles. Here, you can exactly recover the signal back without losing any information. That's a little counterintuitive, which means these points uniquely determine this curve. I mean, the reason because it's a band limited. Now, in physics, there's also called uncertainty principle, Heisenberg uncertainty principle. That's exactly the same. Uncertainty principle was discovered by Heisenberg in 1930s. So you can see truth, always truth, right? Okay, if you look at, this is called a Nyquist theory. Nyquist actually first realized, this is called a Nyquist 1/. Now, it turns out the crystal case, I looked at previous slide, crystal also, if this is A, this is 1/. So nature like this Nyquist interval, A and 1/, reciprocal space. The crystal, if one unit cell, right, salt, for example, a few atoms, sodium chloride, and if this is A, this should be 1/. It's exactly the same. But of course, the crystal, when you measure diffraction pattern, the signal cannot be measured, the phase cannot be measured, okay? So only the magnitude now. So we can get directly, but from here, we cannot get it back. Right? So that's actually phase off. So this actually, this is called a black sampling, no phase and cannot get it back.
Sorry, I'm confused. Can you say again what is this Shannon sampling theorem that?
So Shannon sampling is a signal. That's time t, okay? This is time t, function of time. You have a signal, let's say you type email, okay? Then this signal, okay, you actually digitize it. You actually digitize, okay? The signal digitized.
But you digitize it at a certain bit.
You digitize it actually in reciprocal space. I mean, all the signal, signal propagates actually, so you just need sampling those points, basically, of the Fourier transform.
But this is a finite number of points.
The finite number of points. Yeah, this is a finite number of points. Yes.
But then, of course, you're not recovering the signal fully, right? You're only
you actually recover the signal fully. Well, now, of course, it depends on the resolution, how resolution you want. Okay, here's the resolution, right? You have a certain resolution, like this is so. Of course, if you want a resolution become infinity, then we can find infinite number of points.
The resolution is 1, basically.
Yeah, resolution, you can define the resolution. The resolution defined, and the bandwidth, the bandwidth, the time determined, then these points determined. It's a finite number of points. This is clear, right? If any questions, raise your hand, okay? Is it good? So far, so good? Okay. So here, from here, you cannot get the signal back, right? That's the problem. That's a phase problem. This is a famous phase problem. So it turns out, so I can do another demonstration here. Just use my laser point. Okay, this is a coherent wave. This is a surface, okay? If I shine, I don't know if I can successful. So if I shine laser on this, so you can see the interference pattern from the cell phone, okay? If I scan it, you can see that there's a bigger peak, there's some small peaks, okay? Which means there's some structure on the surface, okay? If I scan it, you can see the pattern actually, I'm shaking, okay? I have some coffee, but trust me, this also will change. The reason is because that corresponds to the Fourier transform of the surface. Now, in principle, if your eye can the phase retrieval, you can directly get the surface of the structure from a cell phone at the resolution limited by the wavelength, which means 200 nanometers, 250, yes?
But in crystallography, like, how much does it matter that those crystals that you might have, like, you may not have like a grain of salt, you might have like a dozen grain of salt. Like, do you count on the fact that it's somehow aligned?
Yeah. So that's a good question. So older days, you need large crystals, but now the X-ray more powerful, you use small crystals, again, very, very small crystals. I mean, the crystal has to be lined well. Otherwise, the diffraction peak will be kind of broadened.
But I think his question is whether you cannot use three crystals lying around, right?
You can, people can actually. So you have to index them. So because a crystal HKL, so you have 3 index. As long as the index for HKL, so you have 2 crystals. Nowadays, people use hundreds of crystals, same try to determine structures. Because the crystal getting small, damage it after maybe maybe a few angles. So you can use multiple crystals. People do that. Isn't it? And so the problem is how to get a phase problem, right? Phase is an important problem. Now, I told you there's a different phase techniques have been developed, and I think Angus is going to talk about it's phase retrieval use different approaches, use focus beam at different defocus, match different images. But I'm going to talk more from diffraction space. Okay, even diffraction space is different phase techniques, including Dirac method. Actually, 2 mathematics can approach Dirac method on the source of the crystals, Herb Hoffman and Jerome Carl. And also holography is another phase. But I'm mainly focused on this, non-crystalline. Okay, so it turns out in this case, if you have 2 signals, right, same band limited A. Now, if you take a Fourier transform, you only measure the 1 over. Mathematically can show you can infinite number of signals correspond to the same intensity measurement. This is understandable. If you can use any phase combined with the magnitude inverse for you get signals. But if it turns out if you can measure between 1 over A, measure those points, then in principle the phase information can be recovered. So this actually David Say was my thesis advisor. He actually did some important work, including he was among the first staff member developed Fortran. Some of you old enough, you know Fortran. Fortran was he was the first staff developed IBM. It was IBM Directive Math Division. I can tell you an interesting story because we have time. Okay, actually times I have to be a little quick. So he tried to. At the IBM 1950s, okay, he got a PhD in 1951. So then he went to IBM. So IBM for long history, always hardware. Hardware is here, software is nowhere. And he was software division manager and then also math division manager. He tried to lift this up. He was strong against the give. So IBM at that time, they give this operating system to Microsoft. So Microsoft, the startup, Bill Gates startup, they basically give this to Microsoft. They want to pick somebody to give it to Microsoft, the operating system, because they think operating system would not be important. David said the biggest mistake the IBM made, because he tried to lift the status of the software and the computer, mathematics, but the hardware is always dominated. The culture. So when I was a student, he refused to use Microsoft. Anything Microsoft Word, I have to convert this text file, send him all kinds of stuff. So he and the Bates, it's a very interesting. So their argument, I can write down here. So their argument is following. So let's say you have a function, okay? Just very simple. You have a function like this. Oh, I cannot. So let me just write. So let's say your function is very simple. Okay, a square function. Okay, that's this. I will use A. Okay. So what is the autocorrelation function? Autocorrelation function is convolves itself. So autocorrelation function. Okay. This fx, this autocorrelation function. Autocorrelation function will be something like this. Autocorrelation function is overlap, like you just shift over. So this distance will be 2a. Right? This is what everyone probably familiar with. Or the autocorrelation convolves itself. So basically, fx convolves fx complex conjugate. I think minus x complex conjugate, something like that. Okay, so you will get this function. So this distance is 2a. So they are, because now, when you take a diffraction pattern, the diffraction pattern I showed, you shine this, okay, the diffraction pattern, this is diffraction pattern. The diffraction pattern, right, this is diffraction pattern. If take an inverse Fourier transform diffraction pattern, that's correspond autocorrelation function. Okay, this is actually first realized by Patterson, that's called the Patterson map phase. So the argument, both David actually very half-page paper, published paper, he's very succinct scientist, only half page. He said, because, okay, now this function, fx is a, this is 2a, but this take a Fourier transform get diffraction intensity, okay? This take a Fourier transform, no, that's we don't know. Now, because this is 2a, so here in order to get a phase, you are oversampling twice finer, 2 times finer than this case. So 2 times finer than 1 over. That's the argument, okay? But when I was student, I was not convinced. So we had a lot of debate, and this. So eventually I proved he's not right. I'm right. So we actually did a very numerical experiment. So what he did is, he's a very, very careful person. I was in Long Island. I get a PhD physics from Stony Brook. I live in Long Island. He was at St. James, okay? He said, okay, John, we don't need debate. Let's do a numerical experiment. So he, on the computer, he created 500 atoms, randomly distributed, and calculate diffraction pattern at different oversampling from twice, less than twice. So if you're right, you should get all this reconstruction back. So I actually, a few days, I get the structure, I delivered the hard copy, everything the hard copy. I went to his door, and he said, okay, you stay downstairs. He wanted to go upstairs to see the, he didn't want me to see the original image. And then after a few minutes, he came down, he shook hands with me, he said, congratulations, you solved the structure. And this actually, it turns out the structure almost is the same, but in a flippable 100 degrees. I'm going to explain to you. This actually, you cannot tell. From diffraction intensity, you cannot tell original image and flip by 180 degrees. So eventually I come in. So let me just explain to you what our understanding. So, okay, first pictorial representing oversampling. Well, what is oversampling? Oversampling means, okay, let's say do an experiment. You have a cell. You measure the intensity, okay? That's this one, this n, this A 1 over A. You sample 1 over A, right? You get a measure intensity. Now, if you get a phase, you can get this back, okay? But if you do the same experiment, but in this case, the detector, let's say 1K by 1K, n by n. Its pixel size is 20 by 20 microns, right? But here, you do the same experiment. Now, its pixel size is 10 by 10 microns, twice smaller. All the setup are the same, which means you have a 2n by 2n. That's n's 1K. This 1K by 1K, 2K by 2K. Now, if you also measure, so if you, in this case, measure the, now if you can get a collector phase information, this region turns out to be must be zeros. Mathematically, actually, it must be zeros. Right? This is actually mathematically very easy to show. Actually, this is very, so if a Fourier transform is continuous, we always digitize it. So you digitize it, sampling at a Nyquist interview, you get this. And you sampling twice finer. So K from 0 to n minus 1. Rho is R is still from 0 to 1. That's just this is 3D means K1, K2, K3. Okay? That's, and so we just simply introduce a new function. You find this oversampled exactly equal to this. So here you can see Fourier transform different from FFT, faster Fourier transform. Faster Fourier transform, n by n Leo space, n by n reciprocal space. Everything is perfect. It's fast. Everything is orthogonal, right? So this is a Fourier transform. But here we just pad zeros become FFT. But you can see this equal to this Fourier transform equal to this equation. Transform, which means if you can get a collector phase information, right? So this should be zeros surrounding the densities, right? So the oversampling, FK is called padding 0 to low if you can collect the phase information. This is clear, right? This is a little mathematical, but for most of you, it should be very straightforward. Yes?
So are we still thinking about crystallography here, where there's periodicity?
Without periodicity, no.
No period.
No periodicity.
Okay.
Yes, no period. We got a single unit cell.
Gotcha. Okay.
Okay, this is good, right? Okay, and then that's actually one of the paper I published when I was graduate student. So if you get it, so basically want to solve low from this FD, the discrete, we call it D discrete, right? This is just a regular sampling case. Now there's trivial phases. Low, I cannot distinguish this one from this one. This is kind of you flip 100 degrees. You can substitute this equation, you get exactly same diffraction density. Right? This is actually very trivial. This is called trivial phases. And you can shift this and get a shift this low, and then you will get the same. Right? And then now let's just say low is Leo. Leo, then this should be central symmetrical. Okay, they got Hermitian symmetry. Yes. And you can, so this actually, when I realized we can count the number of unknown and the number of equations. So in this case, the number of unknown variables, n squared, and n cubed. The number of the, I think it's, the number of the equations, because it's a low from 0 to n minus 1. So one dimensional n, two dimensional n squared, three dimensional n cubed. But the number of the independent equations, because central symmetrical, is n over 2, n squared over 2, n cubed over 2. It's clear, right? If this is complex, then the number become doubled, and this also doubled. The diffraction pattern is not central symmetrical. So somehow, if you have more unknown variables than the number of equations, you cannot solve the phase. But if you do oversampling, so if you're oversampling in this case, you dramatically increase the number of independent equations because but the unknown variable is still the same. Remember, we just pad zeros. You collect the phase information, just pad zeros. So in this case, you see, the one-dimensional is same, two-dimensional twice more, three-dimensional 4 times more, same as a Leo case or complex case. Is it good? So far, so good, right? So in this paper, we introduced the called oversample ratio, the total number of pixels of voxels, divided total number of unknown valued pixel voxels. When sigma larger than 2, then the number of independent equations larger than unknown variables, then so in principle the phase is embedded in the diffraction intensity. Yes?
But this oversampling or equivalently padding the zeros, this introduces artifacts, right?
No, so that's the one thing. So which means the zeros, you pad zeros, it's correspond. You have to measure the intensity. It's not for free. So in math, you can pad zeros. You can pad infinite zeros. But which means you have to measure. In this case, like you have to measure diffraction pattern. Okay, let me just show the example here. Okay. So when you measure this diffraction pattern, you have to find a small pixel size to measure diffraction pattern. Finally, simple space. So when you measure final, then you can say FFT. So FFT is maintaining the number of the pixels in Fourier space, same as the number of pixels in Leo space, right? N by N Leo space. So it's not for free. It's not. This is why the support is because of oversampling. Think about it. If you sample just 1 pixel, the 1 pixel there's no information. Basically, there's a complexity sensing, you have strong constraint. But 1 pixel you don't get it. Conventional theory, you cannot get it. The 4 pixels you still not. So you have enough sampling. So that to do inverse Fourier transform, let's say get a phase information, even get a phase information, you can, if 1 pixel even cannot use a Fourier transform. 2 pixels, 4 pixels cannot use Fourier transform. I don't know if you answer your question.
So what I don't understand is you have some image or something and you want to, so in real space you would add it with zeros. But then you have this edge, right? Where all of a sudden you have all of these 0 values. And at the same time in Fourier space, this oversampling, that's some sort of interpolation, isn't it? And
yeah. Well, if you think about it, the Leo space to Fourier space is yes. But for all the experiment, you measure the Fourier space intensity. That's the intensity you measured. Yeah. Right? So you measure, it's not an interpolation, you measured that. So you have to sample the final. So this is why because you have to sample final, then you can use get Leo space to get zeros. You get it? It's not from Leo space. Nature gave us a Leo space. Then when we measured, we measured the Fourier space. So what I mean is the support is due to oversample. Without enough sufficient oversample, you don't get support. Constraint, yeah?
So is it fair to say that this support constraint is basically reflecting the fact that you start with a function that you would like to represent with FFT on something of size A, so therefore you need N frequencies, right? Mm-hmm. And so therefore you expect, even after expanding your support, to only be needing N frequencies.
Right, yes.
So therefore you want to filter out the higher frequencies anyways.
Right, well, so support constraints, so this I try to clarify, right? So let's say you have an object, okay? You have a happy face, okay? You're like a happy face. This is support, okay? This is support. That's we call it support. Inside is support. And now in the diffraction pattern, so in our case, so which means you have intensity here. You have to sample this final to get a support. Let's say this diffraction pattern. If you sample it less, the same diffraction pattern, but sample less, you will get this. Okay, you will not get the zeros. So you only sample the final. If you sample further less, you get aliens problem. You get overlap. I mean that's exactly. So here it's exactly make sure there's no aliens, which means you have to sample fine. It's no free lunch.
But sorry. So when you say that the middle picture, this man is equal to the diffraction pattern, there actually you are assuming that you're representing this man with just the fast Fourier transform information.
Yes.
That is, you have actually already, I mean, there is some aliasing going on automatically, right? Because you have, you've cut off all the higher frequency, so you've fixed the resolution at that point.
Well, the frequency here, the 1 pixel, exactly corresponds to the frequency here. So this is actually no frequency loss.
Right,
actually.
exactly. But that's the point. That is, you have fixed the resolution at that moment.
Yes, you already digitized, yes.
And so the point is that if you then kind of double the resolution in
But here, the one thing you want to emphasize, the resolution is the same, doesn't change. The resolution, actually, one thing is, this is distance same as the number of the pixel. Let's say this is n by n, okay? This is 2n by 2n. The resolution is the same. The pixel size actually is same.
Yes.
The pixel size is the same. The only just like you get more zeros. The pixel, the special resolution is the same. The pixel size is exactly the same.
So, I mean, mathematically, the point is that these functions which are representing this figure, right? I mean, in the middle point, they can actually be periodically extended outside of the square, and that's why fast Fourier transform works well. But when you do it on the larger square, they no longer are orthogonal, right? Inside that square, and so you get more information out.
Well, but this is still FFT. If paired 0 is still FFT, so this is still orthogonal. Well, this is, orthogonal is FFT.
I meant if you take the function, which is some oscillating function, on the little square and pad it by zeros, these are no longer orthogonal.
Okay, that's fine. Yes. Yeah. Well, I don't know what they define orthogonal. Orthogonality for the FFT is always orthogonal. Okay, fast Fourier transform it's orthogonal, right? It's complete and orthogonal. So here, just you pad. So one thing, in math, you can pad zeros. So you can pad infinite zeros, but here you have to measure it. So for the experiment, you have to measure it. Without a measure finite, if you use 1 pixel, there's nothing. You have to sufficient. You can oversample. You sample the Fourier space such that sample finite, then you can get this. I don't know if this is actually very critical because our community, there still some people. I think most of them are convinced, but some people still. But the support is not for support. I actually will show some experiment data. You have to sample the finite enough, then get support. And you support the finite and the finite if you can get the correct space information. This is same spatial resolution. This is zero pattern getting larger and larger. So you have to sample finite and finite. Is it okay? So in principle this can get and. Now you may ask why? How can you remember unknown variables of independent measurement more than equation doesn't guarantee this uniqueness? So there's actually a paper published in 1972 by Barak and Sodian, two Russian. So they use 1D case is not unique, and 2D, 3D case is a unique. This is related to the factorization of the polynomials. Now, okay, this is Fourier transform. It's very simple. I can write down this a polynomial. I define AJ equals to low j, okay? Kj is in the Fourier, okay? And Z define E 2 pi I kjn, right? So these equations become polynomial. Now, one-dimensional polynomial, usually can be factorized, as everybody knows. You can factorize to this, right? And then f star z equals to 1, because this is exponential function, so it becomes 1 over z, okay? So we can do factorize, you can get this. Right? So far, so good. And mathematically show that if you measure intensity, you cannot, these are all equivalent. Okay? Fz and constant times Fz is constant complex Ez and this equivalent. Okay?
F of 1 over z.
F of 1 over z also equivalent, yes.
No, in that equation, it should be, the middle equation is F of 1 over z times z to the n.
You mean this one?
Yeah.
F1 over z, yeah, maybe you're right, yes.
Right, because you want to invert and then shift back.
Yeah. So then the intensity equals to Fz times F complex conjugate z. So you got this times this. So in this case, there's actually the multiple solutions because the switch zj, so which is zj, 1 over zj are both solutions. So for each pixel, you can have two possibility. So there's in principle 2 to the n multiple solutions. That's indeed, actually, if that's the case. But the 2D, 3D, in that paper, they show is pathologically rare. The two-dimensional 3D polynomial usually cannot be, the factorization is almost pathologically rare. It's not that's still possibility, some special symmetry, very symmetrical object, okay, very special samples in the case. So that's actually the kind of, I thought it's very interesting work from factorization of a polynomial. Is it good? So far so good. So then, okay, that's then the computation aspect. How to compute the computation, the algorithm at FinUp, there's also Gertberg Saxton before FinUp. So all these. When I was studying one read FinUp's papers, he was talking about the shape of plates because at that time no explaining at what condition this phase can be recovered. So I introduced the oversampling ratio that as I thought it is still standard with time. That's correct because it's numerically can be verified. I'm going to show experimental can be verified. Look at it. I read many of the papers. If you wanted to know all the different shape of plate, it turns out the shape doesn't matter much. So the algorithm started with that. Okay, this is a measured experiment measured. You can compute it on the computer. You can generate a random phase. So you have a 2D by 2D, like 2D array. So each pixel you can have a random phase from 0 to 2 pi. Okay, so you get this. The inverse fast Fourier transform get a structure. This structure is nonsense, right? Because the phase is wrong. And then you apply these constraints because we know if you oversample, there's support. You have to oversample. So you cannot just pad zeros, get a, that's just cheating, right? You have to make sure the number of equations are more than unknown variables. And you modify this. If it within the support, and it's the pixels are positive with the positivity constraint, finally kind of positive. And we retain this density outside support. We slowly push it to zero. And use the algorithm, it should be better to slowly. If otherwise, you get a stagnation. So you slowly push it to zero if it's outside support or negative, and then get a new structure, right? New image, and then you do faster Fourier transform, you phase. You update every time you update the phase. So usually after a few hundred, and now there's a review articles. I'm a part of what there's many different algorithms has been developed. And so here I'm going to show some numeric simulation. So this is actually the oversampling. I took a 2D image, I cropped some region. I sampled it exactly without oversampling. I sampled it Nyquist black 1/A. I sampled it 1/A. So I didn't oversample. And this sigma go to 4 because this region is larger than, so the total region divided by this, there's a structure actually, there's an image, is 4. You have 4 times independent equation and unknown variables. Reconstruct beautifully. 3, 2.2. So 2 is our limitation. Actually, when you get noisy, 1, 2.5, you can see the square getting smaller, right? The square getting smaller. So again, and then this is oversampling. If you're oversampling, you just sampling finite Fourier space, and the 2.5 getting. So when I approach it to 1, after smaller than 2, the algorithm converges very fast, but it's not unique. You get a completely incorrect solution, right? And okay, so far that's the hope I convinced you that is that good? So good. Now this is technical coherent diffractive. All this iteration so far, you need coherence. So what is the coherence? Mathematics you don't deal with coherence that much, but for physics that's very important. Coherence we call it the special transverse coherence length (LS). Which means if this source size A, this distance x, the coherence length has to be x distance, lambda divided 2 pi a. Okay? So now this is a coherent source. The sun is incoherent. This light bulb is incoherent. Because if this coherence length of light bulb is very, very small, this is very, very large, like a few meters could be. And there's also temporal coherence. So when the wave propagates, because there's always delta, there's cannot be delta lambda equal to 0. That violates the uncertainty principle. So after distance LT, this becomes 180-degree phase shift. Okay, this is called a temporal coherence length. So in our case, actually, we have to make sure the sample is smaller than the coherence length. Actually, we got the coherent. And with a single, this is actually this is a comparative shift to physical science. This expensive machine, this costs close to $1 billion each. It's APS, spin 8, they built this about 1.5 kilometers surrounding a mountain. This is built in the 1950s. Orange plans completely moved the mountain. It will cost $20 million. But then the stock crashed in Japan. The mountain's still there. I said, what do you do with the mountain? Grow mushrooms. They grow mushroom. I actually once pick up a mushroom with them to go climb the mountain. So this all the facility, and this X-ray free electrolyzer, Stanford is European. This costs more than $1 billion probably to generate coherence. Now this is $10. The other one's $1 billion. Why? Because X-ray, it's almost impossible to get a cavity. The index of diffraction actually is smaller than 1. So in order to use, you have a complete new way to generate X-rays, X-ray lasers. This is called X-ray laser. Okay? And you can see, if you know Moore's law is 12 order of magnitude in 6 decades, if the coherent flux is dramatically increased. This is why this technique, all these CDI techniques, tychography, CDI, becomes so important because coherence dramatically increased. It's just exponential. It's a 20 order of magnitude in 6 decades. It's never ending because X photons, the X-ray or the boson, you can completely increase. Okay, so here's the actual first experiment. When I was a graduate student, I did at Brookhaven National Lab. This is SEM images, 1 microns. This is oversample diffraction pattern, right? And then, actually, there's a movie. Actually, I didn't. Well, I saw there's a movie showed English, but anyway, it doesn't matter. So here's the reconstruction, and here's the convergence. Okay, the convergence here. There's a different way to converge. You can check the difference between the calculated intensity and the measured intensity, or you can outside support and inside support. The density outside support divided inside support. Okay, and you can converge it. There's some oscillations because of noise, but eventually converged after a few hundred iterations.
Wait, is it noise or is it just oversampling?
This is noise. Well, if there's no noise, oversampling, you can get it very sharp. You get almost 0. It's a noise.
Okay.
If any question, raise your hand. Okay, so, and then I also did it. For this same diffraction intensity, I did it. I downsampled. Okay, this is oversampled quite large. This is oversampled actually more than maybe 20. Okay, I downsampled the diffraction pattern to equal to 5, which means this divided by this area divided by this area is 5. The largest square divided by small square is 5. Okay, and is reconstruction good? I downsampled it. When I downsampled it, okay, when I downsampled this, right? And you can see the resolution is the same because I can maintain same spatial resolution, right? The resolution is determined by angle. The angle, diffraction angle is still same. But you see, this square getting smaller. This is the same. Does not change because the same spatial resolution. So this 0 is getting smaller. I downsample. So this is still good. This you still can see it. And this is completely just not right. I'm after a bit smaller. Yes?
What is the limit on the sigma? Like how big?
So sigma, based on previous analysis, sigma larger than 2 means the number of the equations, the number of independent measurements more than unknown variables. So sigma has to be larger than 2.
So anything larger than 2, but it seems like 2.6 is not as good.
Yeah, not that good because of noise. If no noise, you can probably still. But there's noise. No, you have to usually for experiment we always a few times larger than 2. Yeah. They actually mathematically, this community, I haven't, there's quite a few people, still some group from some leading mathematicians, they're still working on this. At the World Country Mathematics, you and the legalists should. Actually, I'm as a physicist, I'm from physics perspective, but from mathematical perspective, there's some people, actually quite a few people, quite a few papers, actually. If you want, I can send you these papers. Even nowadays, still, for the first workshop, there's some mathematicians talk about more legalist proof, but in general, this is correct, this way.
So if you increase the number of pixels, but keep the same sigma, is it the same or?
Well, so what you could do is you want to keep the same sigma, reduce the pixels, and the resolution getting smaller.
No, what I mean is that imagine you have a similar problem, but just many more pixels.
Yes.
So you have to do the same reconstruction for more pixels, but you choose the same sigma. Is the quality of the reconstruction, does that depend on the number of pixels or not?
Not much. Not really. Not as I know.
It does not improve with the number of pixels.
No, doesn't improve with. Yeah. Yes.
So you said you measure the diffraction pattern, but then in order to get these images, you do a discrete Fourier transform, right? So if sigma is small, that means you do get errors on the periodicity of the Fourier transform as well.
So we in our iterative algorithm we always use FFT. We don't use DFT. We always use FFT. So when we which means we undersample this. In order to change sigma, we have to undersample. For example, we bin, 2 by 2 binning. Okay, with 2 by 2 binning, which means reduce sigma by a factor of 2, or a factor of 4 actually. You bin 4 pixels including 1, become 1.
Yeah, but what I mean with these images here on the left side, A and C, and on the next slide, all of these 4 images, you plot these images by performing a Fourier transform. Doesn't matter here, P or FFT. The discrete Fourier transform, FFT is discrete Fourier transform 2, right? Then you get these images, but if sigma is small, then you have the edge of your image close to the edge of the entire image. So you do have the periodicity of the Fourier transform, which means this way you also introduce an additional arrow for a small sigma. This, just in this representation, I'm showing these images.
Yeah, I don't know because of the, well, you're saying because of the array size is smaller because of DFT become.
No, just because this ABCDEF image is not periodic.
Well, no.
I don't think so. I mean, I think it's the problem is really how well determined his problem is in Fourier space. Because what he is putting is the problem to reconstruct the phase under the assumption that outside the dotted square, the signal is 0. And that is what, from what I understand, that's right. This is what gives you the extra information to retrieve.
So for each iterative algorithm, we always push outside it close to 0, okay? So it's still periodic function. You say DFT is all periodic function, but periodicity, you have the periodicity always like this. But this periodicity doesn't affect the inside the structure normally constructed.
So is it correct to say that basically you replace, so you formulate the phase retrieval problem like this? You give me the absolute value of the Fourier transform.
Yes.
And you tell me that my signal is actually 0, identically, on a certain region inside the original sample. And then that is enough, that problem turns out to be enough to reconstruct the phase.
That's true. So there's 2 things to make it 0. One is you have a beam, right? You get the beam can define. So the outside there's no beam. And there's no, I will also talk about tychography. Tychography uses overlap. So basically the concept, the independent measurement has more than unknown variables. So other techniques, you can use overlap. Now actually then you can look at the extended object. You don't need 0 outside.
But for these pictures, it's exactly what.
Yeah, for this, I mean a finite object. You can use either the object finite or the beam is finite. Yes?
This, is true to crystallography. It's also like well established in like digital holography. Are you aware of any specificities of the 2 fields that would not have been like studied equally or like?
Yeah, very much so. Because my PhD advisor David Sayer, he was a pioneer for the Dirac method and crystallography. I thought he should have gotten a Nobel Prize. He was not. The reason is he, after did it first, his paper actually not looking back is the most important, 1951. He went to IBM. He stopped working on it. So Dirac method, for example. So Dirac method is actually very interesting. Dirac method, crystallography is only sample at black peaks. But in this case, you have to measure intensity between the black peaks. So when it's not a crystal, the crystal intensity between blacks is very, very weak. But if it's a non-crystal, intensity more continuous, just like I showed, there's still speckle patterns. You can measure the finer. So basic idea is, if you measure the finer of the intensity, for regular Fourier channel, crystal is a special case. From mathematical point of view, periodic function is a special case, right? General function is not a periodic. For general function, the Fourier transform, you can sample the finer, actually the phase can be uniquely determined. So that's for the difference between crystal and this non-crystal case. And the holography is completely different. Holography is use objective wave, reference wave, get interference, and get from reference wave to get the phase. That's complete.
Well, not exactly. Like there is an imaging technique where you take a coherent light beam.
Yes.
You let it diffract on a sample,
Yeah.
and then with the camera you sample the far field of the Fourier domain,
Yeah.
and then you basically set yourself up in a situation that is extremely similar.
No, let me explain to you why. The original global holography is like this. So global holography, you have a wave coming. You have object here, okay? So object is scattering. The wave coming is object wave, okay? So here, original global holography 1951. So it's a near field. It's a near field. You cannot do far field. Okay, that's fact. And so then you have to get a phase. The phase actually, so you have to, so basically reference beam to direct beam, you have to get interference. But look at the CDI is like this. CDI, we have a beam coming, we have object here. We don't get interference, it's diffraction. The direct beam actually we blocked. Usually we call it beam stop. Direct beam we completely blocked. This beam is about, we only get diffraction from the sample. Here you have to, the coherent wave has to interfere with the object, get interference pattern. Now this is called inline holography. Okay, there's off-axis holography. So this is completely different. Okay, we actually did not use this. So the resolution here is much higher than holography method. The second is inline, the off-axis holography. So off-axis holography, you have let's say you have object here, you have a focus beam. Okay, you have a wave coming. You focus some of the beam here, and then this you get interference. So you have focus beam and get interference. Okay, this can be the far field. But then do the inverse Fourier transform to get autocorrelation function. The resolution actually limited by this point. So resolution is very low. Limited by how small you can focus. The resolution is limited. It is just basic Fourier transform. You get autocorrelation function. Is it okay? So far so good? All right. So then, okay, I'm going to talk about something. Okay, I have another, how to go from 2D to 3D. This is 2D, right? So this actually, after that, then I moved to Stanford. I got an offer from Stanford because they're building X-ray electron laser. I actually got a few offers from different places. I decided to go to Stanford because they're building the $1 billion machine. And they had 500 million, and you got another 500 million Italy. X-ray electron laser, that's perfectly matched. They have, you can see the history of the evolution of this field, right? Early days, no, you need a large crystal. That's one question. The X-ray is so weak, just X-ray generator. It's a large crystal to get interference. Then X-ray getting stronger, stronger, X-ray crystal getting smaller, smaller. So what I want to just one unit cell, just not crystal, right? We are not a crystal. A lot of objects are not a crystal. So one unit cell, so you need to get it small, small. So I went there. So this is experiment I would Stanford we did, and we look at the barrier structure. The X-ray can go through different. These are actually two layers. The STM image shows the double layers. It's actually separate by one micron, so you don't see it. We try to generate some DNA, some similar, and then you can X-ray, you can see it. And then from this interference pattern, okay, this typical pattern. Actually, there's missing center here. Actually, we zoom, you can see that because the center beam is blocked. We don't use it. And then to get a 3D, we measure intensity diffraction pattern at a different angle. We tilt it. So how to assemble a 3D? So at that time, the first paper we did is we just very simple way. Okay, so let's say each one's a pixel, right? We have each pixel. We want to assemble 3D Cartesian coordinates, right? 3D Cartesian from these polar coordinates. These are polar coordinates. So we just use this very simple equation. See how much overlap is larger than 50%. Then you keep it. But there's a problem for this method. Anybody knows what the problem with this method? The problem, the Fourier transform, the intensity variation is very large. The interpolation in the Fourier space is not good. You have a question, Elisa? So this one, we still get a reconstruction. This is the first 3D CDI. Actually, you get the top layer, bottom layer, they separate by 1 microns. That's still reconstruction, but it's very noisy. You can see, compared to 2D reconstruction. 2D reconstruction, you can see very sharp, overlapped. But the 3D, it's because that. So I think mathematically, there's many ways. This is a very simplest way, okay? And so after that, this field really pick up. This has become rapidly growing. I'm gonna so Angus Kirkland is going to talk about electron. Electron also, CDA tachography has become, especially tachography, become really important. And not only just also, I recently attended this Caltech. There's computational photography conference international. Also the visible light. This is just like a computation lens is better than physical lens. Period. This will become even more important in the future, no doubt. So this is actually the review articles we wrote. There's different, the plane wave CDI, the Bragg CDI, I'm going to explain what's Bragg, and tychography, and I'm going to briefly introduce more X-ray field, and Angus is going to talk about the electron, and he have done beautiful work on the electron. So, and there's other form, and we all use iterative algorithms, okay, different type of iterative algorithms. So let's say what's Bragg? Bragg CDI just, you have a crystal, this stereochemical crystal, you have coherent wave, you measure this surrounding one black peak. You can, if interference, you can see it's very different from in the older days, just one broad. But if a coherent wave, you get interference surrounding this black peak. It's become non-symmetrical, and this actual information can be used to map out the 3D shape and the strain tensor. So this is actually mainly done by Ian Robinson, one of the co-organizers of the workshop one. He will give a talk. So Blacksea, I just give you some kind of, because this is a tutorial, give you some knowledge, and you will hear this more in detail, okay? And even in the deep learning, how to apply it. There's actually a lot of activity in deep learning to phase retrieval. Can do, at least as, right now they can approach the iterative algorithm. I believe kind of better. Deep learning kind of better. We actually have a paper on it. I'm not going to talk about it. You will hear more in the first workshop, okay? And they can also recently, this is actually now more than 10 years ago, they can map out the displacement, 3D atomic displacement field. Okay, this actually should be vector in the vector field. But so basically, Bragg CDI is you use a crystal, you measure the coherence interference surrounding one black peak. Okay, you can measure all the black peaks, so you can map out the strain tensor. Now, another technique, as I mentioned, called tychography, also kind of scanning CDIs. Now, tychography, the tycho means overlap. It's from Latin. Graphy is writing. Okay, overlap writing. Well, originally proposed in 1969. Okay, but that's actually more for crystal. You overlap black peaks, the overlap. But the modern version is really by John Rodenberg, and Angus and Peter and Nalist also did a very important, some pioneering work. They are among the. So John Rodenberg actually used X-rays. The reason why, because electron coherence is still not as good as X-rays. X-rays, boson, electrons are fermion, right? So he did X-ray experiment, and so here just you overlap. You just overlap. Overlap can help to increase independent measurement, maintain the same amount of variables. That's exactly just an oversample. That's just different way. It's a very smart way, right? You just increase the independent measurements because this overlap. This region can use constraints, and then you can reconstruct both magnitude and phase. And the advantage is you can use extended object. You can look at all the object. You don't need to be the finite. You don't need to be a finite beam, right? And then also a few years later, and a year later, and Pierre Thibault, and he wrote a paper in the Science, and it can not only reconstruct the image, the complex wave, but also the probe. Now, this is actually very new. There's a probe, he can reconstruct both. This actually is, this kind of zone plate, this kind of periodic circular, concentric circle, the magnitude and the phase, can reconstruct both the magnitude and phase, and also the probe, they can reconstruct probe. Because the overlap is just a lot of redundancy. Imagine, you dramatically increase the independent equations, right? That's just the concept. They can see very similar to oversample. You just increase the dramatic increase overlap. The larger the overlap, the better. And here I show one example. This actually, you can see, you get a diffraction pattern, and this is diffraction pattern. Okay, you scan it, you get individual reconstruction, you patch them together. Actually, it can be randomly, do individual reconstruction pattern. And this probe is not updated. Actually, now algorithm can also update the probe to after very easily converged. And some groups using tychography or use deep learning to find this, get from diffraction pattern to this, and also the probe. In the workshop one, you will hear some talks. This is a really great field. How to use machine learning to deep learning to solve this kind of problem, because this is, you can think about it, right? Physical lens and the computation lens are so much powerful. It's application free. You can Ming also Stan also talk about means working on, or you can get a super resolution. So it's just like you can get so much more information. It's okay, so far so good. And it's also, this measured diffraction pattern, this one merged, it's really a unification of microscopy, conventional microscopy, diffraction and computation. So, and deep learning, now it requires deep learning. Deep learning, hopefully, then you can do it simultaneously because the physical lens advantage is simultaneously get the image. But the deep learning can almost get some of that. So this is what you get all the things. But this needs still more work. This has been working on, and hopefully, I'm sure other group also work on. So I want to go. Talk about from 2D, combine CDI with tomography. I mentioned we try to patch this intensity, map the 3D intensity. It's not good because of the intensity variation. So hopefully, maybe some of you interested. That's, I think, still a direction to go. But so far, we have most community have used combined CDR with tomography. Tomography is well-established problem, and it has been CAT scan has been widely used. And me and Stan, we have been collaborating for a while. We developed a different method. It's called generalized Fourier iterative algorithm. So I actually borrowed some of the CDI algorithm to tomography and made a big impact. In the second talk, I'm going to individual atoms because I borrowed some CDI algorithms to tomography. And this is one of the algorithms, not the latest one, latest is even better. So we get images, right? We take a Fourier, with a Fourier gradient, with oversample, we get it in the Fourier space. And then we use the iterative algorithms. The iterative algorithm between Liu and Liouville space. So the phase retrieval algorithm trying to find the phase. But here, we are trying to find these unknown variables because we cannot measure all the projection. There's always signal-noise ratio limitation. There's a radiation limitation. So in this case, we only measure certain limited number of projections. We cannot get all. But the algorithm try to iteratively try to find the best structures that are consistent with the measurement with some constraints. The constraints is so we can use a general constraint. For example, if I reconstruct a human body, I can define a box, right? This box should be 3 by 2 by 2 meters. If someone outside the box, it cannot be a human. That's based on definition. So 3 by 2 by 2 meters, and it should be positive. You cannot have a negative density in your body, right? That's so those are very general constraints. Yes.
Has anybody tried? Because we do it for holographic techniques, but has anybody ever tried to create a deep learning model that would directly infer the three-dimensional structure from the set of rotated raw data frames?
That's very good. I mean, nobody, to my knowledge, maybe people working on it, nobody has got results close to the iterative algorithm.
I mean, right here on this campus, I think the lab of Aidan Elskin
okay.
has some work in reconstruction of images, but in the case of digital holography.
Okay.
So I would like to think that there is a world where that type of operation, specifically because it's very similar to the prior techniques we use in holography, where you start gathering the information from the real domain and the Fourier domain. There might be a step there.
Yeah, I think this is another direction. How to get a directly use deep learning. I think this is just another important direction for those people, and especially young. And this great field. This is so broad applications of tomography. And we actually compared with biological vesicle numeric simulations of Jianwei with equal slope tomography. I developed one when I was at Stanford. Actually, at that time, I had a good chat with David Donahoe. Many of you know Donahoe is a big shot. So we had a lot of chat. I collaborated with one student. We developed equal slope. And then field back projection, that's used to have a hospital in a CAT scan. And this simultaneous iterative reconstruction technique. And you can see, okay, it's not very clear, but the Jianwei is much better. I mean, our iterative algorithm can perform much better. Okay, you can know more information in the paper. So I just want to show the 3D reconstruction, and then I can end. And so I'm going to show one example on this combined CDR with tomography. We did the same simultaneously cryotachography and fluorescent microscopy green algae. Okay, this is done at Argonne National Lab. This collaboration with Chris Jefferson. And this is a diffraction pattern. This is kind of very, completely different from biological cell. But this typography reconstruction at different angles. The phase, this is phase information, okay? And this simultaneously will measure the fluorescence of the different elements, okay? This actually can be different elements. And this here is a potassium signal. We get it. Then this is typography reconstruction of the typical reconstruction of the 3 different projections, and phosphorus, sulfur, calcium, potassium, and they actually in that different origin. This is a different organ. The phosphorus, calcium, sulfur, and potassium is more uniform display. Also calcium is also in a different organ. And then we did reconstruction, okay, using our Gen 5 and the feedback projection is just not non-iterative. It has been. And especially the missing, like this one, the number is very noisy because phosphorus is very noisy. You see, this is a missing wedge direction. Now, missing wedge, you cannot tilt plus minus beyond, no, typically 70, plus minus 70 degrees. Okay, this missing wedge is well known. Electron tomography, X-ray, you see, this is almost elongated because the data is not measured, then it's smeared out. But here we can still reconstruct very well. And even this projection can more details. You can say calcium, and then we also can our algorithm can automatically angular refinement, because when you do experiment you kill the angle. This is not exactly accurate. There's instrumentation error. There's all kind of error, right? But we can automatically angular refinement. We find each projection how much deviation of the angle, and you can see the green versus the blue. This after refinement is. The blob should be vascular, more kind of spherical. So there's a lot of development. I mean, of course, deep learning has a lot to learn to taking care of all this. There's a lot of detailed stuff. Not only just signal noise ratio, missing data, right, angular refinement, how this. And then after we can do 3D correlation structure of the fluorescence. This actually we can use Gen 5 with different phosphorus, calcium, sulfur, chlorine, potassium, and this is typography reconstruction. Okay, and then we can put them together and get a different organelles. This is actually I thought this is important. This is about 10 microns. It's too thick for electron microscopy, and we can see all different organelles with different elemental distribution. Okay, so I kind of my last slide. I want to thank my. Just go back to my. Okay. How to? I push. I just push the. Let me just do. That's good. Yeah, good. Yeah, how many minutes do I have? I'm done? Or you want to hear more, or you want a coffee? If you want a coffee, I mean the last slide, or I can talk about something was controversial, but eventually turned out to be, I think I was right. Okay, I just feel a few minutes. So in 2010, we published a paper in Nature. That created a lot of debate. If you look at our Nature website, there are some comments. The whole community, CDR community, thinking, no, it's not right. Let me tell you, what is that? So we call it ankylography. Ankylous means curved surface. Now I stand here. I can exactly see Elisa sitting in the first row. I don't need to turn around. I'm not moving. Angus last row, Dima is second row. I can see it. So your eyes have 3D vision. Why? Why your eye can give you third dimensional information? Your eyes, X, Y dimension is better than the third dimension. Because otherwise driving you'll be crazy, right? You cannot drive if your eye don't give a third dimension. So why is that? The reason because now also your ears, the distance is larger than 2 eyes. Why? Anybody knows why? Your ears distance larger than, otherwise it doesn't look good. The reason because the wavelengths of the sound wavelengths, it's longer. In order to get high resolution, you're going to see it, okay? This distance, the larger the better. You can Z-dimension information better. So you can identify. So if you go to LIXC, right? If I call you Elisa, you will immediately turn to me, or Dima, you can immediately turn to that, yes?
Is there evidence that we sense phase and sound, what you're saying?
Oh, absolutely.
Yeah?
Absolutely. I mean, just look at what the way your earphones project to you when you watch a movie and you feel that the door is opening behind your back.
Yeah.
It's all done with phase differences between the ears.
Interesting.
Yeah, phase actually more yeah, actually. So this actually curved surface can give us third dimension information. Now, so if you have a spherical wave, now actually there's a confocal. Confocal is a convergent beam, but actually here we talk about diffraction wave. So there's 2 theta maximum. So x, y resolution determined by this. Z actually can see this as z dimension information here because of the spherical wave. If it's a complete plane wave, you don't have z dimension information. So now we don't use a Plaxial approximation because in the Fresnel-Fraunhofer diffraction, Plaxial approximation, then there's no such term. So this actually, we did some simple experiment, soft X-ray, and we measured it. Because CCD is a plane wave, it's a planar detector, but we have to put in a curved surface, project to resample the curved surface. And this actually really constructed. There's we got a stick figure, it's a test pattern. And we can get a z dimension information. The z dimensions, the resolution is lower than xy. Now the reconstruction, this you pose the problem because you won't get a 3D information from the 2D projection, right? It's a yield-posted problem. You have to use all the constraints. Okay, it's a mathematical yield-posted problem. And now there's actually quite a few groups working because there's a lot of advantages. Even though I recently went to this photography, computational photography, because the cars, all the self-driving car, all they want is 3D information. The camera, they want to capture 3D information. And there's also a paper by Van Dyck and Fulong Chen. They use actually also curved wave. Basically, use spherical wave can give the 3D information. That's actually really traced back to this. There's quite a few papers recently published. Now we put all the code here. Because at that time it was very stressful because people think you're right. Then we decided to put everything online. Since then we put everything online. Code, the source code, the data. Okay, then I just finally want to thank my collaborators and my group, my current and former members, some of them sitting here. Okay, and my collaborators, I have some wonderful collaborators, including Margaret Monay and Henry Captain, and Stan. Stan actually, we have shared some students, including Min and Elisa, have Saman and Yishan also here, my postdocs. So we have all the codes here. So everything we put online. You put online or put on website. Okay. So as I mentioned, Angus will give Wednesday. I think Wednesday, right? Tomorrow morning he will go to more related. Okay, he will electron aspects, and I will give a second talk on more electron tomography related. Paul and will give a talk. Paul Voice. He will give a talk and related to my second talk. Okay. Thank you for your time.